thank you. Thank you for still being here in the second lecture. So, given a number of questions I received during and also after the talk, I decided to do a brief summary with the slides, and in particular start with this. So, let's remind this. What is the Laplacian? So, as we said, for a C2 function, we can define this operator, which actually sends a function to a measure, okay, as this one. You take the Laplacian, you put Lebesgue, okay? But you have to remind that it's a differential operator. Now, if I have a function now which is only integrable, I define its Laplacian by duality, okay? So I take C2 function with compact support, and now, essentially by Stokes, I define its DDC, the DDC of G, here. Okay, this one, anyway, by duality with this one. Now, the example to have in mind is if I take the Laplacian, complex Laplacian of the function logarithm of z, okay? So this function is harmonic outside of the origin, okay? But it's Laplacian. This is the fundamental solution of the Laplacian. So the measure is the delta n 0, okay? Now, so what we call, so I will also define the name for later, is that we say that log z is a potential for delta n 0, okay? So now we have a measure and its potential. Now, more generally, every positive, yes, sure. Oh? What do you mean, sorry? No, DDC is the measure, is delta 0. The function is the potential for the measure. So the function, so in general, so let me take the second line. If I have a measure, so every positive measure is an average of deltas. So I just do by convolution. And so the point is I have nu, and I obtain u here, such that, so this is DDC. So from the function, I can go here taking the DDC. And from the measure, I have an explicit formula that integrates the solution of the delta against the measure. Okay? So this is completely parallel, one another. I couldn't talk about positive measures or potentials. Now, but which potential? They are not all functions. These are the subharmonic functions. So you can think of subharmonic functions, essentially, if and only if, for today it's enough, their Laplacian is a positive measure. Okay? Think of them as convex function if you want on R. Okay? Now, so this is really the key. This is we want to think of them essentially as the same space. One is the positive measure, one is subharmonic functions, okay? And by moving with the Laplacian, one is the other. Okay, so this was the tool, I mean, that I introduced last time. Notice that if I have this measure, Laplacian of u, okay, and I push forward, if you do, for example, the example with the delta n 0, if I take the measure delta n 0 and I push forward, this is the delta in the point f of 0. Okay? I push forward the measure, okay? Keep the mass, a point goes to the next point. So in particular, if you see this with this definition, you see that for every measure, it's equivalent to push forward the measure or push forward its potential and then take in the DDC. Okay? This seems very trivial. Actually, rewriting this is true, but it means that this operator, the Laplacian, commutes with a complex structure. It's not true in general for a smooth map. Okay? I'm really using that f is holomorphic here to make this commutation. Now, so now as I said, now I'm making a summary of the first lecture. So the goal that we had, if I have to state in a slide, is this. We are given a rational map on P1, or a polynomial, as we said. We are given another function of some regularity. We will see which one. And we want to study this operator. It's called transfer or Ruelle-Frobenius operator. We want to study this one. In which sense we want to study this operator? We want to find a norm, which means we want to find a Banach space, on which this operator turns into a contraction. Now, there will be an invariant line. So actually, it cannot be completely a contraction. There will be an invariant line. Okay? For example, if you take phi equals 0, the constant are left invariant up to the constant d. So, and outside of this, you have exponential contraction. Okay? So this is the goal. And you want all this picture to depend analytically on the parameter. Okay? This is the goal. Notice that the dependence of this operator on phi is highly nonlinear. it's linear in G, okay, so it's a linear operator, but it's completely non-linear in phi. And actually, it's not by chance, if I iterate this operator, this appears here, the sum here appears at the exponent, and it's essentially the reason for which studying this operator is the same thing. I mean, it's what can be used to study the statistical properties of function. Because here you see a Birkhoff sum. So in some sense, if you can study this operator with some phi, and you can perturb a bit phi, here you can study the statistics of this one. Because once you study this, you understand more or less how it's going, this Birkhoff sum. Could be a computation, but we don't want to do it now. So this is the problem, okay? We want to study this operator. Now, we introduced some notion. As we said, every polynomial on C has the main property, which is a branched covering. So every point has D preimages, counting multiplicity. Okay? And now I have these two operators, and maybe I received a question, so I want to make sure. When I talk about duality, I'm talking about duality not between function and function, say the Koopman operator, given a reference measure. No, I'm talking about duality between a function and a measure, okay? So in this way, if I can pull back measures, in this way, instead of doing this, I can do the pullback of 0, which means I take 0 here, I have its preimages, there will be D, and now I sum over these preimages. Okay? This is the pullback of this measure. It's well defined because I have a covering. And this operator on measures is dual to this operator here on function, in the sense that if I do f star on that measure again a function g, this is nu again f star of g. And this is the push forward, is the sum of preimages. I wrote there with the level n, okay? Okay, maybe I forgot the n, but it's this one. Now, once you have this, now let me state the first theorem that I kind of presented, as an introduction yesterday. If I take this system, this holomorphic system, polynomial or rational map on P1, you have a measure, an invariant probability measure with a number of, it's canonical in the sense that it satisfies a number of properties. The support is the Julia set, but we define the Julia set as the support if you want. And the point is that for essentially every point, you can think on the Riemann sphere. You just have to exclude 0 for z square, or example like this. It's a really finite number of points. Then every point you can take like this. You take pull back of this picture. You renormalize by D at every step. Okay? So every time you have a probability measure, you have a limit. This limit will satisfy this Furter property, because you do another time and it will keep true in the limit, is the unique measure of maximal entropy. This convergence is exponentially fast when tested, for example, against older, let's say, C2 functions. I will tell later more about this, so I don't rewrite what this means. But the convergence is quick against regular tests. There is an explicit way to find that I presented one, let me say, I presented a way to say that the Lyapunov is positive just as a motivation to define potentials and these things. There are much easier proofs of this. This maybe was better to say. Then I say that there is a formula for the Hausdorff dimension and relating the entropy and the Lyapunov. In this case, the entropy is just log D. But this formula is true in general, we will see later. And actually, today I start moving a bit. I will do everything in dimension 1, but I want to start moving in the direction of higher dimension, because lecture 3 and 4 will be in higher dimension, okay? So while today I will say and write mostly in one dimension, I will start saying when everything I'm saying is true in higher dimension. And this theorem is true in higher dimension, okay? What does it mean higher dimension? Is the generalization of rational maps in higher dimension will be defined precisely in lecture 3. But this is the theorem. For context, I mean, the Brolin result was the first convergence for polynomials in the 60s. Then it was generalized by Lubitsch and Frey-Lopez-Magnier in the 80s. And so this is the start. The speed is in the years 2000, 2020, 2010. Okay. Now, we have this picture. We said at every step I pull back measure. Okay? I have a tree of preimages, and I'm averaging. Now the question is, instead of doing this picture, I also take my function phi, and at every step, not only I take z1, z2, z3, for example, but I multiply by some function here evaluated at this point. Okay, and I continue. Here will be, I don't know, let me call it phi, I don't know, z2, 1 for some pre-image, plus phi z2, delta z2, 1, to say that I keep going with pre-images. Okay? This I continue. But the point is that I'm summing this in the exponent, okay? Now I'm perturbing at every step, and the perturbation depends on the point I have, okay? I'm accumulating the weight here. Now, it's not anymore true that what I will get will be invariant or this, because the operator is not such. Now, of course, if I take this with phi constant, is the problem as before. And in the other opposite direction, if I take phi completely regular, measurable, I cannot do anything, okay? So let's say with some regularity on phi that we take. I move to this weaker regularity that I defined yesterday, which is log Holder continuity, okay? Instead of just taking Holder, which means that a scale R, it's essentially R power gamma, I define a function which is log Holder. Let's say this gamma Holder, and this is, let's say, Q log Holder, which at this scale is log R power Q. The 1 plus is just to make sure that, I mean, this is at small scale. This is to make sure of the diameter. You don't care about the 1. Now, Holder functions, of course, satisfy this condition, okay? These are weaker than Holder. Now, I moved this. Now, if you do this process, it's still true that this process converges, okay, to some limit measure. And you have a convergence like this. So for every point, actually, you always go to the same measure up to some renormalizing factor that you have to find in the procedure. You don't know a priori what it is. But you have some limit measure multiplied by a number, which, notice this, it's the starting point, z. Okay? So if I move the point, it's always the same measure at the limit up to a constant, okay? And this constant can depend on a starting point. Now, the point of this theorem is that, writing in this way, so I have a limit measure here, and if I take this function rho, I call it rho phi, times m phi, this is mu phi. I denote in this way, this function is this measure is invariant, okay? This function rho, as we said, satisfies this property. This is the operator that I said before in the previous slide. The other measure satisfies this. Now it's an exercise that you write down. If I have these two conditions, if I take the product of this function times this measure, this is invariant, okay? This is a standard exercise. And this measure, now, yesterday motivated a bit more, but maximizes not anymore the entropy, but the pressure. It's another functional. Now, this one maximizes the sup on all invariant measure, let's say of this plus integral 5 nu. Okay? This is the function which is maximized. Okay? So you change the problem, I put phi, I generalize the one before. Okay, so the theorem that I will mainly try to describe today, at least to give some idea, is the following. For every f, a rational map, polynomial like this, also this holds in higher dimension, I will get to this later, there exists a norm for which I can fix two parameters. I can fix one gamma here and one q, okay? And for every gamma and q I take, I can find the norm in between, which means I can take the norm to contain all their functions, okay, one by one if I want, and I can make it very regular in the sense of q, taking q go to infinity. And on the Banach space defined by this norm, I have the spectral gap. Of course, the line spanned by rho is invariant. I cannot do anything. This is invariant with this factor. But on the complement of this line, I have the exponential contraction, okay, with respect to this norm. And the operator, I will not focus on this now. I just prefer to try to give the idea of how to get this norm. The operator, everything I'm going to say, is analytic. And the analysis is important for the statistical properties, because it means that you can get statistical property by the theorem of perturbed tensor operator. Okay? So this is the goal. It is for today. It's for now, most of the lecture. So once you have this, you have statistic. And maybe notice that phi and g have really the same role. It's the same space on which I'm taking g, so the Banach space, phi, and so psi, which could be the statistic, the observable, okay? It's really the same space. So phi and g play really the same role in this picture. Okay, so let me, now from now on, the slides don't look the number, are here for support for myself, if I receive questions. So I will, don't look at them, it's not, if I receive a question like I cannot read. So I want to, in order to prove the second theorem, you will notice that this is the reason why I stated the first theorem with log order regularity, because we have to be able to work with function in lower regularity, not only order. Now, let me say right away, so the idea of the norm. So I write here, it will take some time to get there, but at least I stated. This norm on function g, you can take it in this way, is, so for a function g, this is the minimum c, suppose I define this norm, such that dg wedge dg bar, so this is, think of it as essentially C1 norm, okay? For C1 function, this is a C1. This is less than C squared by homogeneity. And now here I would like to put something, okay? If I put something smooth, I'm defining C1 functions, okay? Nothing more. If I put Lebesgue, this is C1 functions. But we know that every regularity I put, like C1, it will be lost after one iteration. I have critical points. Older, it will be lost after one iteration. I have critical points, okay? So the idea here is to put a series, which will depend on, I fix some alpha less than 1, and then here I put the push forward of Lebesgue. This is the first idea. It will not work, but it's in the good direction. So what does it mean? Here I have a geometric series for now, okay? This is a probability measure. This is a probability measure, okay? And the idea is that now this norm is weaker and weaker if f, they said if the critical point of f is more and more recurrent. Because this term, imagine if f is hyperbolic, this doesn't change. If critical points are far, this is smooth. It's still smooth. I'm still using C1 if f is hyperbolic. Sorry? Left? Yes, so this is really the form which is dz as this dz, and this is the same with the bar. I could define this in the same way as Stokes as I defined the DDC, and actually it's before, because I remind that DDC is actually this d times this the bar, okay? This is a weak C1. I want to think of this as the distributional C1. For a complex reason, I need to write both of them with C squared here, but I could write this if you want. But because I want here a measure, because I can control measures. So the idea is this. The more and more f is bad, okay? The less is hyperbolic. The more I have a critical point which is very recurrent. Remember that I don't want to put any assumption on f. The more this is bad. The more with big J, this is very singular, okay? So these objects become bad. Even if the mass is this, this is the mass of this measure. It's, at every step is 1. So all the goal is to say, 2 steps. 1, I can control. Suppose that this I write as DDC of H, all this term, okay? I can control H in a uniform way with some uniform regularity, okay? This is the first point. Second point, I need some control that says that from the regularity of H, I can get some regularity of G. I will go into this in more detail now. But this is the idea, okay? You want to build a norm which works quite well, and it will estimate itself by iteration now, okay? But then the point is that you also have to induce, okay, but this, it doesn't diverge. It does not have to be L1 function. I don't care of L1 function. I need to be continuous in some sense. And then induce the modulus of continuity here. This is potential theory. This is the part that uses potential theory. And I could not do in general, in a real dynamics. So, notice that we will approach this, but Lebesgue will not work, actually. I will have to replace this by a weaker regularity. And actually, this norm to put here, this is the real heavy lifting of the construction, to find what to put here. To find not Lebesgue, but something else that I control very well by iteration, okay? Lebesgue, I lose it. I lose Older, I lose again. So I have to change this. I cannot put Lebesgue. But at the first level, this is the idea, okay? And now I want to motivate to give an idea of the first theorem and see why actually a series appears. Why we have to think that we cannot do this without having a series, okay? Then we will try to estimate the series. But why a series is unavoidable? So let me remind that if I'm doing my transfer operator, if I have to do this theorem, by duality, instead of pulling back points, I can push forward functions by the transfer operator, okay? So what I want to do is to make this convergence. To find that this sequence, L n phi g divided by lambda n, is, let's say, uniformly bounded and uniformly continuous, equicontinuous. Okay, I want to do this. Then ask Oyarzela. Now, I'm assuming here that I already know what is lambda. The problem is a bit more difficult because I don't know what is lambda a priori. I have to find lambda in the construction. But suppose I know already lambda, okay, so it's simpler. Now, to do this, I will just stick to the case where g is equal to 1, okay, to find this convergence, and phi is C2. So every time I will write some Laplacian, it will be done with C2 functions, okay? Then a point is to make it work for less regular functions, but I will just work for this for now. Okay? So what we want is that I define this one here, like 1n is this one, is this iteration. I will use star to say when it's normalized. I want to study this. I want to give this property for this sequence. Once it's this, it's classical that the limit will be only 1, it will be this function rho and whatever. So the point is really to have the convergence. With phi 0, it would be prove that this sequence converges to a constant, okay? If you want phi equals 0. Now comes potential theory. How do I really, what does it mean using potential theory? One of the things I will say is that there is a bridge between measures and their potential, and functions which are subharmonic, their potential, okay? I want to make this bridge very precise because it's what we will need. So the heuristic version of this is that if I have a function, this you can think even in any setting. If I have a function on a ball, and I control its Laplacian, even C2, okay? This gives me a bound of the oscillation of this function, okay? It's a real just integral estimate. Now, one can make this very explicit. So in this case, suppose I have two subharmonic functions, okay? So Laplacian positive. Then the heuristic version is that if I control the modulus of continuity of the second, I can control the modulus of continuity of the first. Let me be more precise. I can do this, but with a slight loss of regularity. It's not true, for example, that C1 implies C1. Well, some cases, yes, but in general, I have to lose some regularity, okay? But we already know that we lose regularity by iteration, so we are not worried by this. But the main point here is that these estimates, they are quite classical, actually. There is not really deep here inside. They are very uniform, which means that if I have a sequence of functions, all bounded together in Laplacian by the same measure with some continuous potential, then the sequence is uniformly continuous, okay? Because I can apply the dilemma altogether. So the goal becomes to say, I can estimate this Laplacian here, so the DDC of this sequence. When I write this, I mean, a priori this is not subharmonic, so it's a measure, I can take positive and negative part. When I write this, I mean, I take positive plus negative part. I want to estimate this with a unique error, which is a measure, which will be the DDC of a function now, and this we want continuous. So if I have this, I will be able by the lemma to estimate the modulus of continuity of every n here. Okay? Fine? So I want this. So I want to be able to uniformly estimate this term with a single measure here, the same for every n. Okay? And with continuous potential. This is the important point. Okay? Not really the series. The series now will come. Now, let's try to develop this Laplacian. This I helped myself, so I will not write at the blackboard. But the point is that the only important point here is that let's keep some parts. Let's really focus on the important term. Is that up to some computation, what you get is that this term actually is less than a series which is geometric. I remind you that this is the term that we took by assumption less than log d. Okay? It could be refined, but so this is less than 1. This is geometric. And here, I have the object I said before. But 1 is not important. Let's say j star of Lebesgue. It's already something that we wanted to study here. Okay? This comes from here. If I'm already trying to estimate in a uniform way this sequence, I get to the series here. Okay? So now the question is, I have a geometric series of measures. Each of one actually is the push forward of the previous. I don't know here the potential of each one, I don't know. But is it true that this measure here, the mass is fine, is up to this constant, the mass is finite? Can I estimate the oscillation of the potential, like uniformly at scale r, the modulus of continuity? This is the problem. Then, why I want to explain this? Because once we have explained this, then we can try to find the norm in which we can really estimate things. But before having done the step 1, it's difficult to do step 2. Okay? So let's try to do this, to see why I can estimate this. It's a series of functions. Now, here I described potential before. Lebesgue has some potential. Okay? So let's say that more or less, this is the DDC of some function. It's nothing more than z square on C, if you are work locally. It's smooth. This is a function. Now, as we said, if I push forward Lebesgue, this will be the DDC of some uj, I don't know, but which is the push forward of this. Okay? Some functions. I know that at every step, I lose regularity. But I know in a controlled way. So if the first is C1, the next will be older, let's say with gamma, which is, I lose the D. Sorry, what did I do? Sorry. So if I start with, suppose for simplicity the degree is 2. I start with a C1 function. The image, the push forward, will be 1/2 older. The next will be 1/4 older, 1/8 older, and go like this, okay? So the first part of the lemma actually is clear. It's at every point, at worst, I lose the older regularity that I can lose. The tricky part is the second. This function here, a priori, I have nothing better to say that they go like d power g, because it's a sum on preimages. Okay? They diverge a priori. I'm summing on preimages. So a priori, in norm infinity, they could go at this speed. Okay? It's the best I can do a priori. This is the point. One can prove that actually I can make this still going up, but arbitrarily small. Still exponentially, but arbitrarily small. This is the point here. The norm infinity of this potential, okay, diverges as slowly as I want. Okay? So this is class. I mean, this is just computation in charts. This I'm using already some result. Here I'm using complex analysis. Okay? This is something in complex analysis. I'm using this. I will do a more precise version later, so it's I skip this. But now, once I have this, notice that I have the series. Now it's an exercise. It's a nice exercise. If I have a series of geometric, each term I control in older words and words, but I know that they go to 0 geometrically in norm infinity, now I can estimate, not an older norm, of course, because it's weaker than everyone, but I can estimate in log p for every p. It's an exercise. You cut the series at the good size, and you estimate the tail with just a norm infinity. This means that for every p, my series here that I wanted to estimate here has potential, which is log p. Okay? So my series of terms, actually, I have a very defined well modulo. It's not older, but it's log p for every p. It's enough 1p. I don't care a lot of them, but it's uniformly continuous and bounded. Okay? So this is really the idea behind. Now we want to quantify this. But if you got this part, now it's to get to this part to be more quantified. But this is really the idea, okay? You have a general lemma that says, if I can bound the regularity of this function here, I can bound the regularity of this function. Okay? Up to small loss. Notice that there was a small loss. You remember? There was a small loss here. A square root. I would lose all there. Log p that doesn't see the square root, because if I estimate, if I do the regularity at scale log r, if I can put a square root, it becomes a constant. I don't see it. So this lemma works very well with log order estimates. Now, so this is done. We are very happy we did this. It's true. At least we kind of proved theorem 1, it means. I at least explained the idea of why we can have a uniform boundedness and equicontinuity of this sequence. Now, once we have this, then it's classical. But now that's the main point. How can we quantify this in order to take a norm for which we take g and phi in the same norm now, and I have contraction in that norm? Because notice, for now, it's like if I'm taking g1, or if you want, I can take smooth. Phi, I take smooth, and I did a convergence in log p. If this had to be the norm, I have to be able to take this log p. Okay? Or if I want to use older, I have to improve this to older. And we saw that there is no way to go above older. Okay? So the norm has to be weaker than older. So now the idea is, let's try to lower the regularity here, okay? And possibly improve a bit the regularity that we got from this one. Again, with something depending on f. This will be the point. We will try to estimate the series itself. Now, so when started talking about norms, I didn't tell you, but actually there is a very, relatively simple norm that one could use. It's kind of unrelated to the problem we are talking about. But if you remember, I said that U is subharmonic. U is subharmonic if and only if the DDC of U is a positive measure. I could define a norm of subharmonic functions. I could define a norm of U, subharmonic, let's call it, as the mass of this one. The mass as a measure. I could define this as a norm. Now, subharmonic are not a vector space subharmonic functions. Minus a subharmonic is not subharmonic. But I could take the space of difference of subharmonic functions. U, let's say, is U plus minus U minus subharmonic. This space corresponds to what? Corresponds to DDC of U is a measure with sign. It's a sign measure, okay? Instead of just subharmonic, I take differences. Now, here I can put a norm, and the norm is essentially the mass of this or the mass of this. Suppose I take the sum. On P1 by cohomology, they will be the same because it's a cohomology reason, but take the sum of them, okay? Take that I take as a norm here. I can define this, let's say, the mass of the DDC U plus DDC U minus. Or if you want that this is nu plus plus nu minus, I take the mass of nu plus the mass of nu minus. So, I cut the measure in 2 parts, okay? I do the best I can, the best decomposition, and I do this. And now notice that this norm contracts very, very easily. Because in cohomology, I have a gap. It's very simple. Because measure by push forward do not increase in mass. One point is sent to a point. But functions increase by d. So if I can find a way to estimate the growth of function by a growth of measures, I win, because I gain a factor 1 over d. Precisely I can do this. If I push forward the function, it's DDC. I can compute it. If now I take a function g, and I have to take the f star of g and I take the DDC, as we say that this is f star of DDC. This is nu plus my nu minus. So at worst, I use this decomposition, this and this. So this norm does not increase. By definition, it's there, it doesn't increase. I can use the same decomposition because this keeps the mass. Now I have the factor d, because remember that my operator, the lambda, is d, is f star over d. So I gain for free a factor 1 over d of contraction, okay? So this norm contracts. Why it's not so useful for the other theorem? It's useful as a step, because this norm is on subharmonic function. There is no relation between subharmonic and older. Of course, C2 functions are bounded in this norm, okay? Because the Laplacian is a smooth form, I can decompose. but they have no relation with older, okay? And even worse, if you try now to estimate the transfer operator instead of F star, now it's a nightmare. Because F star commutes with Laplacian, but not the transfer operator. If I try to do this, I have to do F star of E phi multiplied by G. This is the transfer operator. And if I try to develop, I have all kind of mixed terms that come out. And the moral of the problem is that DDC of a product, G of H, is bad. I have the term DDC of G times H. I have the term DDC of H times G, but I also have mixed terms. This is the simple reason. If I try to do it, this is essentially a product of two functions, and then I try to do the commutation of DDC. This is the problem. I cannot use this norm if I have this space here, okay? Now, for most of the construction, for simplicity, I will explain what happens if we could use DDC, but this is the reason of this one. I already put it here. The reason why here I don't put a DDC, it's because of this problem of the products. So if you try to develop, as we said, the operator DDC, and by consequence, every norm you build with the operator DDC is a complex operator, okay? It will commute well with F star, but you kill completely the complex structure if I multiply by e power phi. On the other hand, we know that F star, yes, this operator here, so multiply by e phi is not a problem for the regularity. If something is older, I multiply by e power phi, it stays older. It's not a problem. But F star has the problem with the regularity because it kills older and whatever, okay? It keeps killing. So, and we already know that we cannot use older. So we have to at least try to combine two norms. One will work well from one side and one from the other side. So the idea here is to cook up a norm which will have the DDC inside. Okay, otherwise I will not be talking about potential theory here. We'll have DDC. We will use the potential theory to bound this norm, but we add some regularity, and we do it in a way that each part will help the other to get more regularity. This is the point of the balance to get, okay? You don't want to put too much, otherwise you will lose it, and you don't want to put too low, otherwise it cannot help the other one to get the regularity to stay. So, since we already saw that this norm is not bad, actually. We don't want to completely destroy it. And also log P was not so bad, actually. It worked quite well. Let's start with a norm, which is the sum of the two. I could define this norm here. I write it here, P, which is, in some sense, the mass of the DDC, which is the difference of subharmonic part, plus the regularity. Okay? I could define equivalently on a measure, saying that this is the mass of the measure, plus, let's say, the potential, the regularity of the potential, because we say that functions and measure are the same thing, okay? So when I talk about this norm, I could define here or here. Now, this measure is really the heavy lift of the problem. Here I will replace it. We will not use Lebesgue. We will use some S, and S is a measure bounded in this norm. This is the point. Now all the problem becomes proving that in this norm, maybe I don't have a contraction. But at least things diverge very slowly. Because then in this series, I will be able to kill it. I will be able, once I have something that doesn't diverge too much, inside the norm, I will be able to estimate with itself. But I need already some a priori estimate on S, okay? On this norm here, P. Okay, so this is the first checkpoint. Notice that pluripotential alone cannot work. Pluripotential theory alone cannot work because there is a transfer operator perturbed. Real regularity alone cannot work because you lose the regularity at every step. We are trying to mix two of them. And we are already starting with two parts, this part and the log P, which have some good property, okay? This is just the idea to keep until now. Now, let me say right away that this problem, whatever it means, it's not a problem now, this problem of the products. I don't want to focus now on this, so I will say this is fine. But let's just think, if I try to again develop my Laplacian of the operator and whatever, Just look the red part, only the red part. It's the one we had before, okay? I erased, but it's what we did before. It was this one in practice. Was the main part to estimate, okay? And let's now try to estimate, assuming that phi is bounded in this norm. Okay, I have a series, it's a geometric series. Just look at the red part. Now, this geometric series, you can prove, before I told you the growth of the potential was slow in norm infinity. Actually, you can improve. This is slow in norm log Q, log P, or whatever, okay? Arbitrary slow. So the series that I estimated before, not only I could use it all there and then norm infinity, actually I can use log P at every step. For the first term, I say, okay, the log P become big, and the tail is still, I can prove that the tail is still going to 0 exponentially. Notice that this is already a theorem that says the exponential mixing is true with function with this lower regularity log order. Okay? And we use this in the tail. Now, imagine that I just want to estimate the regularity of this red part, a geometric series times this function. Okay? This one, now I apply this Boff-Lemon theorem. For the first part, I estimate in this norm, which grows very slowly. The last part, I use this one, exponentially small. It's the idea we used before for the series just with order, okay? But now it works. Now I can estimate this term. What's the problem? If I start with log P, I will lose some regularity. It will become log Q with a bit less regularity. It will not be the same because each one of them will be worse, 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 and then I use norm infinity. So if I start with Q, P, I will have some Q explicit, but less. So it's true that I already improved. Now I have an exponential convergence here to 0, good, but in another norm, but it's already better. I don't have a spectral gap for now, but I have 2 norms, if you say, and if I take test and weight in the first, I have exponential contraction in the slightly weaker norm. Okay? It's already an improvement, but we get there to get to the spectral gap. Okay? So this is not a spectral gap yet. Now, the main point now is essential to use this one. As soon as you realize that there is no way to have a sum of term and to try to estimate itself, you try to inject the sum in the series. Sorry, the sum of the series, the sum of the series in the norm. And you try to put the same series that you keep having there to estimate, and you cannot estimate, you put in the definition of the norm. So let me define now this norm for measures for now, okay, for measures. I say I bound this measure by a series of this form. For now it's for measures, so this forget, it's not function. I have this series. Okay? Again as before, what do I want? But I know from this, what is it? Yes. I know that by definition, if I shift, I want to estimate f star of r in this norm, this is less than 1 over alpha, the norm of r. Alpha, I can take it close to 1. So this norm is bounded and diverges very slowly by iteration, okay? It's what I wanted from this norm. Now, this is obvious from the definition. The less obvious part is that if you take a series like this, but it's more or less the argument we saw, this is log P, it has good control in series, so still the potential of the left-hand side, the potential of R, is log Q. So this norm, the non-obvious part, is that it defines a compact space of continuous function. Okay? What? S is one measure with this norm bounded by 1. Any. I want to, yes, there exists S, like this. For some, this is that one, you see? I bound my measure with a series, dynamical series, but at the starting one, I don't take Lebesgue, because it doesn't work. I take this thing which is almost Lebesgue. It's like Laplace unbounded and log-Holder potential. Because log-Holder works better, because of these lemmas before. Because we see that it works better. Now, so the non-obvious part here is that this norm, suppose that I define the DDC of G in this way. So this is the norm. The regularity of G, okay? Now what I use DDC of G is less than a series. If I can prove that this series has a good potential, by the argument I said, also G will have a good potential. This is the argument we just said, okay? So now we know, actually, this norm is bounded by C2, if you want. because C2 it's enough that you take the first term. And bounds log Holder. So it's already good, it's there, it's a compact space. Now, if I try to run the machine now, estimate this term, notice why I'm keep saying that I want the compact space, because now I want to go to 0, not bound. Suppose that now I have all this term to estimate. Now the red term will help me, because the series is bounded. But uniformly, this by induction will go to 0 if I am on a compact space on which I have the gap. So this will go to 0, the series will go to 0. This term, I don't care, it goes to 0, and so it will go to 0. So this norm, I have a hope to have the gap, okay? But I build it, first of all, with a norm which a property of slow divergence, okay? And then I embed it in a series, which is dynamical, to kill the problem of the loss of regularity. Now, there is a problem in doing this, and the problem is that, but it's a small problem, we didn't consider this fact of having the Laplacian of a product works bad with all these terms. And this is the reason, it's a bit technical, by why instead of DDC, you have to put this here. Because this norm here, if you don't put a DDC, works well by product. The point is that in all the computation I wrote, I always skipped the term which are mixed derivative of the two terms. And this you cannot estimate with the two Laplacians. So, up to defining the norm in this way, which is the one I said here. So, it's a weak C1. Now it's not a weak C2, it's a weak C1. If you want to call it a dynamical C1. The first term is C1, if you want, but then it's C1 bounded by something, and then you continue. So this norm is bounded by C1. Now, this one now works very well, okay? There is, a priori there is a gap. There is just one problem, was a small problem, why we didn't want to start with this at the beginning. Because from the very beginning, I told you, you have to use this lemma. DDC less than DDC, then you have a bound on oscillation. Okay? If now I change the operator on the left, it's not anymore a DDC less than DDC. Okay? It's not anymore subharmonic, subharmonic. Now, this is more complicated to get. It's still true. This is, again, this is not dynamics. Okay? It's a lemma completing complex analysis. That one can still get the regularity here, up to some loss that is quantifiable, we don't care. But the point is that if this is log Q, this one will stay log Q with some other Q. Okay? So this is not a problem. This one you can get it. Okay, so what's left to do? We have a norm now. This norm, as I said, this norm, I call it alpha p, now is less than C1, and is larger than log Q. And it has the gap. Okay? Now there is just one last step to do because we wanted to contain all their functions and not only C1. There is just an interpolation. So this is true. Now, before I said all their functions are those that oscillate at scale R with their power gamma. You can define all their function actually in another way, which is this by interpolation. You can play this game. I take a function G. I cut in two parts. One is small in norm infinity, epsilon small, and I check if epsilon go to 0, at which speed the part, say, C2, goes to infinity. If this is polynomial in 1 over epsilon, this is older. If this is exponential of 1 over epsilon p, this is log Q, this is log p, okay? But in the same way, so you can define all their function by interpolation between continuous and C2 functions or C1 function, okay? So in the same way, now you take this norm that you have, that bounds C1, and you do interpolation. Now this is standard, okay? But now by interpolation, I get a norm. Let's call it alpha p gamma, that now is bounded by C gamma. And this is the point. It's still bounded. This is not killed by the interpolation, but some Q prime. Because I have to check that this will stay good by the interpolation. This is true, so it's not the problem. And now we really have a norm which contains, with bounded by the older norm, bounds a compact space, and for which we have the gap. But again, the real idea here is this. And I wanted to start, if you want to, even if it's false, the real idea is doing this, is to try to estimate this term. Yes? Huh? I interpolate between norm infinity, continuous function, and this alpha p norm for which I have the gap. In the same way as I can define the older norm by interpolation between C0 and C1, I use this norm as a weak C1, and now I interpolate to create another norm which is between C0 and C gamma. Okay? But in the definition of the interpolation, instead of using C1, I use this. So we'll get something which is bounded by this, actually bounded by C gamma, and still bounds continuous, actually log Q, because all the estimates are log Q. Yes, it's this. This is not it's just because I wanted to get to older and not C1. But the previous one already had the gap. Okay. Okay, so this gives the gap. So what I said is true, actually in higher dimension. There is essentially one reason I didn't explain in higher dimension. It's because every time I wrote a DDC, it will not be a measure. It will be a 1-1 current. So here you have to actually use positive closed currents to make all the estimate. All the modulus of continuity estimate that there was here were not on measure, will be on currents, okay? I prefer to skip this part, okay? I hope at least someone here will be happy of this. And, but this is true also in higher dimension. In higher dimension, there is a genericity condition that if you want, I can enter in this detail, but it's not relevant now. But the statement is really the same. Okay, so I think my hour goes to the end. So in the next two lectures, actually Mary will present the generalization of the other theorem that I said in dimension 1, the theorem of Magnet, which is this formula between entropy, Lyapunov exponent, and Hausdorff dimension, and to a generalization in higher dimension. Let me just state the theorem, so we are already thinking about what she's going to talk about, and then she can start quickly. So for every measure with entropy larger than k minus 1 log d in dimension k, notice that in dimension 1 it means positive entropy, okay? We can define a dimension which is not the Hausdorff dimension, it's another one, but which satisfies the Magnet formula. But just that you have to put, instead of the Lyapunov, you put a sum of the Lyapunov exponent. It's a dimension which sees the volume expansion, and Vd is because of this, is the volume. Now, some comments. First is that one can ask, okay, but are there measures with this property? Well, all the talks I gave today was to present a class of measures with this property. Of course, there are many, many more, but every measure which we constructed has entropy larger than k minus 1 log d, because it's the same computation in dimension 1. At most, the integral of phi makes you lose a log d. Okay? You have this. More generally, it's enough that you have a measure with positive Lyapunov exponent, so it's well defined, whatever in the denominator, and you don't have to touch to give mass to the post-critical set. Notice that the difficulty in higher dimension is that the critical set is not finite, it's an hypersurface, okay? This is everywhere a problem in a problem in higher dimension. So this will be something to be taken care of, but it's not finite. And let me just notice that in dimension 1, since there is Magnet formula, this is equal to the Hausdorff dimension, so this Vd should be equal to the Hausdorff dimension. And actually it's true, I mean, this reduced to the Hausdorff dimension in dimension 1. Okay, so I will stop here, and I hope you will be interested on Thursday for the second part of the talk about this theorem. Okay, thank you.
Thank you. Are there any questions? Daniel.
So you have this norm that you invented between the holder norm and the other norm, right? So when this norm that you invented coincides with the holder norm?
When f is hyperbolic.
If only if?
Yeah, you see, because the point is here, I always, in order to use this criteria, I always worked on C. You could say, actually, I can just work on, I just care of what happened on the Julia set.
Yeah.
Now, if f is hyperbolic, when I said there is a singularity on the critical set, if this critical set is far from the Julia set, on the Julia set, nothing happens on the regularity. So if f is hyperbolic, this is against C1.
Yes.
Because all the singularities are outside.
And how about, is there any situation where the norm coincides with the lower bound? because you have this.
No, I don't expect this because the lower bound, you lose it. I mean, it's by iteration, you lose it. It's even log Q, in general, you lose it. I don't expect it to be, no, I don't expect, I mean, for hyperbolic, again, you could use any of them with hyperbolic.
Can I ask one more question?
But in general, no, I don't expect it to coincide.
So one more question. So how about rational maps where the Julia set is the whole thing?
Like it's the same.
It's the same.
I have no assumption on F. No assumption on F.
But in this case, you know something about, for instance, if the post-critical set is finite, I suppose that is very
in this sense, yes. So here I explained a method that works for every F, okay? If now you start asking, what if I put some hyperbolicity in the system, like Misurevitz map or Collet-Ekman, this can be improved. This can be improved. For example, if it's Misurevitz or Collet-Ekman, you don't need to put this condition on the oscillation. You can take any bounded function or whatever. It can be improved because this is a method designed to work without knowing anything about F. But as soon as you know a bit of regularity, of expansion of F, yes, it can be improved. So it's, yes, and generalize the class, and yes. So it's, in particular in that map, if the Julia set is all the sphere, then it's post-critically finite. If it's this case, then yes, it can be much improved because all the singularities that you have to study are in a finite number of points at that point. It's only there. And so you can actually redefine this as a norm with just some weight near the bad point, and you can also go with this. But this is really to handle the general case with infinite critical set, recurrent maybe.
Other questions?
No, I just have a comment. So the mechanism that leads to the spectral gap in the real setting, it's always having some sort of hyperbolicity of the transformation of randomness. So here this is replaced in the complex setting with this norm that that this DDC part of the norm that you build.
Yes, it's really that in the complex setting, you have some a priori estimate that if you want, you can call it like this, that once you have a series like this, you can prove actually that it bounds something. This is the difficult part here is always the left part, is to prove that this is not some crazy regularity that you don't control, that it bounds something regular. And this is the complex setting.
Yes.
This is what in general will not be able to do in the real setting.
Yes. And so the results are the dynamics, it's a polynomial or a rational map, you said. Can it be more general than this, just a holomorphic function?
But you see, holomorphic function, let's say in dimension 1, if you go to transcendental, I don't know. I mean, it says no. I'm using really the fact that every point has deep images. It's finite degree. It's finite degree. So it can work in higher dimension. And what I'm saying as higher dimension, maybe it's not what, I mean, not for now. I'm not talking about the diffeomorphism in dimension 2. I'm talking about a rational map in dimension 2, which are systems which are expanding in 2 directions. So if you always have a property in general like a covering of a given degree, this works. The real property behind is the covering. And a bit of complex structure to define the space of subharmonic function, because it's well defined in the complex. Very likely. It's not written, but quite likely. Yes. There are a couple of points technical, but it's not.
All right, other questions? All right, well, let's thank Fabrizio again.
Thank you for you.